All right, in 6.2, we're going to continue our discussion of the normal curve. There's two types. There's a standard normal distribution and there's a non-standard normal distribution. So this question asks, what's the difference? Well, in a standard normal distribution, we have it's normalized. So the center will always be at 0, and then this will always increment by 1s. So this is the standard normal. A non-standard normal could have any numbers down here. So we might have, let's say we have the mean height of men or something, so in inches. So we have 68, 70, 72, 74. And then on this side we have 66, 64, 62. So for a non-standard normal, we can have any numbers on this axis. And they're going to have units too. So in this one, I have to know that these are in inches. Okay. And the problem with the non-standard normal curve is that I would have to have a separate table like this for every new curve that I looked at. So I'd have to develop new curves, new tables, depending on my units, depending on what I'm measuring, which is impractical. So what we'd prefer to do is transform the non-standard normal into the standard normal. So we're going to transform this. And it's very easy to do. We're going to do that using z-scores. And we've already seen how to calculate those, but we'll get a lot of practice today calculating them again. So these are z-scores. And in fact, that's the whole goal of section 6.2 is to take non-standard normal curves and transform them into standard normal curves. So what is the difference? The difference is that the standard normal curve, the answer is B here, has a mean of 0 and a standard deviation of 1. So notice the mean is just the center of this, so mu is 0 in this case, and sigma, the standard deviation, is 1. Over here we had a mu of 68, and I just came up with it, just kind of made it up, a sigma of 2. So these incremented by 2. And then the second part of this says, while a non-standard normal distribution has a different value for one or both of those parameters. Okay, so that's the theory. Let's take a look at one of these. So we have IQ scores. So find the area of the shaded region. The graph to the right depicts IQ scores of adults, and those scores are normally distributed with a mean of 100 and a standard deviation of 15. So they tell us mu is 100. Standard deviation is sigma. They tell us that's 15. And we want to find the area of this curve. So the first step is we have to transform this curve into a standard normal curve. So to do that, we're going to use z is equal to, our z-score, x minus mu over sigma. So let's box that equation. We've seen it before, but... And in this problem, I have to do this twice. So I have an x1 here and an x2. So I have to do this equation for both those x's. So let's call this z1 would go with x1. So it would be x1, which is 70, minus mu, which is 100, all divided by sigma, which is 15. This would be negative 30 over 15. This is minus 2. So in our standard normal curve, we're going to actually look at this area as being minus 2 to whatever this other one is. So let's find this other one. Z2 would be x2, which is 110, minus mu, which is 100, all divided by sigma, which is 15. This is 10 over 15, which is 0.67. So this would be 0.67. And we want the area between these two curves. So this goes back to what we worked on. So now this problem is no different than what we did in section 6.1. So now that I've transformed it, we go back to what we did in section 6.1 to find the area between two z-scores. I take the area of the bigger one, the bigger number, minus the area of the smaller number. So what we're going to do is look up this. 0.67, which is going to be all of this area, minus -2 minus that area. And again, if you can imagine taking this area and subtracting this sliver from it. So if I subtract out this sliver, then I get the area in between that I want. That's going to equal this area here. So we're going to look it up. So we look up 0.67. It's positive. So we go to the positive z-score. And we go to 0.6, which is right here. And then we go to 0.7 in the hundreds place. And we're looking for where those two intersect. So right there, 0.7486. 0.7486 minus, now we go to -2. So it's negative, so I go to the negative z-score chart. And we go to -2, which is right here. And it was -2.00. So first column. So it'd be 0.0228. 0.0228. And if you subtract those two numbers, you'll get the area in between is 0.7248. Okay, that is pretty much what we're going to do today, so we'll get lots of practice with this. 13 is the same idea, but it's just a bit different in that they tell us the area, and they want us to find the original x value. So it's another IQ score. So they're saying find the IQ score that is in the 90th percentile. So their IQ is above 90% of other people. Okay, so we're going to start with the table. So we're going to start with the table. Because x is to the right of the middle of this thing, we know that it's positive z-score. So all z-scores over here will be positive. So we're going to go to the positive z-score and look for this area of 0.9. So we're going to look in this sea of numbers for 0.9. And the challenge is going to be this. I've got a 0.8997 and a 0.9015. So you're probably not going to find exactly a 0.90. So we have to decide which of these is closest. Well, this one's 3, let's see here, tens, hundreds, thousands, 3 10,000ths away from the answer. This one is 15 thousandths away. So we would go with this one. So the associated z-score with this is 1.2. So you go all the way over to the row, start 1.28. So you go over to 1.2 and straight up to 0.8. 1.28. So we know the z-score is equal to 1.28. And now we're going to rearrange the z equation to solve for x. So to unbury this x, we're going to multiply both sides by sigma. And if I multiply this side by sigma, it cancels here. So I pick up a sigma in front of the z. Now the last step would be to add mu to both sides. They'll cancel here. And we'll be left with sigma z plus mu equals x. And I'm going to write that a little cleaner over here. X is your mu value plus your sigma value times your z. We can box that equation and keep it for when we're given problems like this where we have an unknown x value. And in the problem, it tells us that mu is again 100 and sigma is again 15, just like the previous problem. So the actual IQ score that this person has in the 90th percentile would be 100 plus 15 times this z-score that we found, 1.28. And if you do that arithmetic, you should find that this person has an IQ score of 119.2. 119.2. Okay, 14 is pretty similar, but there's one wrinkle. They gave us the area to the right of the x value, but the table that we look up always gives me areas to the left. So you don't actually want to look up 0.55. You want to look up this area here would be 1 minus 0.55, which would be 0.45. So we're going to look up 0.45. Now notice this x value is to the left of the middle. So the middle would be right here. It's to the left of that, so we know that the answer is going to be negative. It should be a negative z value. So we go to the negative z-score table, and we're looking for 0.45, that area. So once again, we look in this sea of numbers for 0.45. Should be towards the bottom right. Okay, here we go. I've got two choices, 0.4522 or 0.4483. And it turns out okay, so we have 0.4522 or 0.4483. This one is 17 units away from 0.45. This one's 22 away. So we're going to go with this one, 0.4483, as being close enough. So the z-score for that would be minus 0.1. And then I go up to the top, 3. Minus 0.1 is the row it's in. And 0.3 is the column. So our z value here is minus 0.13, just below the mean. So we're going to use the same equation. X is equal to the mean again is 100. Sigma again is 15. So it'd be plus 15 times negative 0.13. So notice now this is going to subtract from 100. And if you do this, you will get the IQ score for this person is 98.1. Okay, 15. Assume that adults have IQ scores that are normally distributed with a mean mu of 105 and a standard deviation sigma of 15. Find the probability that a randomly selected adult has an IQ between 95 and 115. So the non-standard normal curve they want us to look at so the center of this normal curve is 105. And they want us to look at a person between 95 and 115. So something like this. Well, just like before, we're going to call this X1 and X2. And so we're going to find Z1, which will match X1, would be X1, which is 95, minus the mean, which is 105, divided by sigma, which is, again, 15. This would be negative 10 over 15. This is minus 0.67. Z2 would be this X value of 115 minus the same mu, 105, divided by sigma, which is 15. Notice these numbers don't change. So this will always be 105 here. This will be 15 here. So for anything I might ask, in this question specifically, these two numbers don't change. And this would give us positive 10 over 15, which is positive 0.67. And so we want to now find, instead of this non-standard normal curve, what we're actually looking for now is the area of the standard normal curve between minus 0.67 and positive 0.67. So this is the area we want. Well, just like before, we have to break this into two problems. One is where we find the bigger Z area. So we're going to find the area for 0.67. Find this area. Then we're going to subtract out the area for the smaller Z value, minus 0.67. And in doing that subtraction, we'll actually find the area between these two. So that should equal this one we care about, okay, so again to the Z chart. So we're looking up 0.67, it's positive. So I go to my Z chart, 0.6 is here, 0.7 is here, so it would be this number here, 7486. 0.7486 minus the negative 0.67, negative 0.6 is way down here, and then 0.7 is right here. So we're going to see where those two intersect right here, 0.2514. 0.2514. And if you subtract those two numbers, you should get 0.4950. So there is about a 50% chance that if you randomly select an adult, their IQ score will be between 95 and 115, is how to interpret that. Questions? Okay. Hopefully these aren't too bad. We're just kind of doing the same thing over and over again, looking up these tables. Okay, 16. A survey found that women's heights are normally distributed with a mean of 63.8, so mu 63.8, and a standard deviation of 2.3. So sigma is 2.3. A branch of the military requires women's heights to be between 58 inches and 80 inches. Find the percentage of women meeting the height requirement. Are many women being denied the opportunity to join this branch of the military because they are too short or too tall? So the X values they're interested in are 58 and 80. So let's first convert those to z-scores. So z1 would be x1, 58, minus the mean, which is 63.8, divided by sigma, which is 2.3. And for some reason, I don't have these intermediate. I have the answers written down, but not the intermediate numbers. But I can do this pretty quick. This should be negative 2.52. Z2 would be x2, which is 80, minus the mu, which is 63.8, divided by 2.3. So again, notice these second two numbers don't change. And if you do this, you should get 7.04. So now we will again look up. Let me not draw the pictures anymore because they take time. So what we're going to do is we're going to find the area for the area of the bigger number, 7.04, minus the area of the smaller one. That's how you always do these problems, negative 2.52. And that should be the area for a z value between those two numbers, negative 252 and 7.04. Now 7.04 is a huge z-score. In fact, we saw this before. For positive z-scores, your biggest number that we have in the table is 3.5. Anything above 3.5, we assign an area of 0.9999, 4 nines. So we're going to say this is 0.9999 minus the area for negative 252 would be right here, the negative z-scores. Negative 25 is here. 252 would be right here. So it's 0.0059. 0.0059. And if you subtract those two numbers, you get 0.9942. So what's the percentage of women who meet the height requirement? 99.42%. So the last step is to convert this to a decimal, or excuse me, a percentage just by jumping this 2 to the right. And so we would say 99.42% of women are going to meet this height requirement that this military branch has. So then the next question is, are many women being denied the opportunity to join this branch? Well, no, because they're letting in 99% of women who meet that height restriction. So the answer is B, no. Okay, part B says, if this branch of the military changes the height requirements so that all women are eligible except the shortest 1% and the tallest 2%, what are the new height requirements? So now they're saying, okay, we're going to let in everybody except for 1% of the shortest. So that would be over here. And that area then would be 0.01, 1%. Or they're going to restrict 2% of the tallest. So this area here would be 0.02. Let's start with this one because it's easier to find. So for this, we need the z-score for this. I have to look in the negative z chart because I know it's going to be negative. In fact, let's write that. We know this z is negative because it's to the left of the middle. And I'm going to look in my CA numbers for 0.01. So negative. And we're looking for 0.01 as our area. Here's a 0.0099 or a 0.102. This one's actually a little bit closer to 0.01. So let's go with minus 2.33. So our z-score is minus 2.33. Minus 2.33. Now to find this z-score, we know it's positive first off because it's to the right of the middle. But keep in mind, my table always tells me areas to the left. So I'm not actually going to look up 0.02, I'm going to look up 0.98. How did I get this number? This number and this number have to add up to 1 because I'm basically looking at the entire curve at this point. So 0.02 to the right means 0.98 to the left. So we're going to go to the positive z-score and look for 0.98 in the sea of numbers. And we get, this is 0.9798, which is 2 units away. And this is 0.9803, which is 3 units away. So we'll go with this one, which is 2.05. 2.05. So this one is 2.05. These are the z-scores for these new height requirements. They actually want the actual heights, the x values. So we would let's call this z1 and z2. So x1, which matches with z1, would equal mu, which is 63.8, plus sigma, 2.3, times this z-score, negative 2.33. And if you do that arithmetic, you should get, for the short side, you have to be 58.4 inches or taller. For the tall side, x2, it would be 63.8 again, plus 2.3 again, times the z2 value of 2.05. And if you do that arithmetic, you should get, for the tall side, you have to be no taller than 68.5 inches. That's a good problem to study because it has lots of, so we're finding areas, we're finding z-scores, we're finding reverse z-scores. We're kind of working all angles of these problems that we could ask you. Okay, 17. Assume that the human body temperatures are normally distributed with a mean of 98.18, so mu, 98.18, and a standard deviation of 0.62. Sigma is 0.62. A hospital uses 100.6 degrees Fahrenheit as the lowest temperature considered to be a fever. What percentage of normal and healthy persons would be considered to have a fever? Does this percentage suggest that a cutoff of 100.6 F is appropriate? So the first thing we'll do is calculate. So X in this problem is 100.6. So let's immediately convert that to a z-score. So it'd be this X value, 100.6, minus the mu value, 98.18, divided by sigma, which is 0.62. And if you do that, you should get a z value of 3.90. If we look up 3.9 on the positive z chart, you might recall that we just got done saying anything bigger than 3.5 has an area of 0.9999. So this area here is 0.9999 to the left of this marker. So that means 99.99% of people are going to have temperatures below 100.6. So that only leaves people that have, so if a person's healthy, but they're still considered a fever, that means they have to be in this area. Well, this area here would be 1 minus 0.9999, which is equal to 0.4 zeros and a 1. Now, the last part is they want you to convert that to a percent. To convert this number to a percent, jump this decimal 2 to the right, and it would be 0. Oh, I think I had too many zeros here. There should have been 3 zeros and then the 1. 3 zeros and a 1. So when I jump it 2 to the right, it would be 0.01%. So there's a 1 in 100th% chance that a healthy person without a fever would have that body temperature of 100.6. So now the question is this a good cutoff? Yes, absolutely. So there's only a 1 in 100th% chance that you're going to diagnose someone with a fever when they're actually still perfectly healthy. So the best answer here is C. Yes, that's appropriate because there's a small probability that a normal and healthy person would be considered to have a fever. Okay, part B now says, physicians want to select a minimum temperature for requiring further medical tests. What should that temperature be if we want only 5% of healthy people to exceed it? Such a result is a false positive, meaning the test result is positive, but the subject is not really sick. So basically what they're saying is they want to pick a temperature over here that only allows 5% to pass the test even though they're not sick, which means they want 95% of people to be correctly identified using this test. And so now we look up this z-score associated with 0.95 to the left of it. And we would get, that's actually a special one. It's got a little asterisk here. So the area for exactly 0.95 has a z-score of 1.645. 1.645. This is a special z-score. We'll see this again in later sections. And so now we're going to calculate the temperatures. So the temperature X is equal to the mu value of 98.18 98.18 plus sigma, which in this case is 0.62, times the z-score we just found, 1.645. And if you do this arithmetic, the temperature that they should use as their cutoff would be 99.20 degrees Fahrenheit. So basically, their fever temperature of 100.6 was too high. So they should drop that down to 99. So they were testing people too often, basically. So if they drop this down to here, they won't have to test as many people. Okay, 18. For the purposes of constructing modified box plots, which we talked about a few chapters ago, outliers are defined as data values that are above Q3 by an amount greater than 1.5 times IQR, or below Q1 by an amount greater than 1.5 IQR, where IQR is the interquartile range. Use this definition of outliers, find the probability that when a value is randomly selected from a normal distribution, it is an outlier. So first off, we have to recall that Q1 and Q3 both separate the bottom 25% and the upper 25%. So we can get z-scores for these two values. So we have a z for Q3 and a z for Q1. Notice Q1 is going to be negative because it's to the left of the middle. So let's look up 25%, because that would be to the left of Q1, and get its z-score. So we're looking up 0.25, and it would be 0.25. Looks like this is the closest one right here, 0.2514. So the z-score is minus 0.67. Minus 0.67. Minus 0.67. Now the nice thing is, because this area is the same as this area, and this is a symmetric curve, this z-score I don't even need to look up. It's going to be the exact same number, except positive. So if this is minus 0.67, this one's going to be positive 0.67. Now, a low outlier is going to be 1.5 times IQR times IQR below Q1. So it's actually going to be Q1, I didn't write this very well, Q1 minus this. And IQR is the distance between Q1 and Q3. This is IQR. That distance in the Z chart, or in the Z scale, would be 0.67 minus 0.67. So let's write it here. IQR is 0.67 minus 0.67, which would just be 0.67 times 2, or 1.34. So a low outlier would have a z-score of minus 0.67, which is Q1, minus 1.5 times 1.34, it would have a z-score of negative 2.68. A high outlier is equal to Q3 plus 1.5 times IQR. So it's 0.67 plus 1.5 times 1.34, and it equals positive 2.68. So by symmetry, again, I get the same number. One's negative, one's positive. So now we're looking at the normal curve where we have a low outlier is over here, that's minus 2.68. A high outlier is over here, that's positive 2.68. And we want these two areas. So we'll look up negative 2.68 and get its area. So we go to the negative z-score. Minus 2.6 is right here. 8 is right here. Where those two intersect would be right there, 0.0037. So this area is 0.0037. By symmetry again, so I'm not even going to look this one up. By symmetry, I know this is also 0.0037 because they have the same z-score. And then finally, what's the probability that you'll randomly pick an outlier? Well, it's this area plus this area. So the probability of an outlier is 0.0037 plus 0.0037, which is equal to 0.0074. Now I might have rounded a little too much here. The final answer is 0.0070. But this is really close. This is 4 10,000ths away from that. Okay, so that's the end of the computation ones. The last two are word problems, so let's look at them. They should be quite a bit simpler. Where would a value separating the top 15% from the other values on the graph of a normal distribution be found? So the top 15% would be somewhere over here, and we'd have 0.85 to the left of it. And so it has to be, they're asking where is it at in comparison to the mean, which is mu. It has to be to the right. So it'd have to be the right side of the horizontal scale of the graph. Okay, 20 says what conditions would produce a negative z-score? Well, a z-score, z-scores are calculated by x minus mu over sigma. So if x is less than mu, I'm guaranteed to get a negative z-score. So your x value would be smaller than the mean. Z-score corresponding to an area located entirely in the left side of the curve. Well, that's also true. So anything to the left of here would also be a negative z-score. So it looks like A is actually correct. A z-score for a negative area. You can never have a negative area. An area in the top 10% of the graph, well, we just saw in the previous problem that that would be a positive z-score. A z-score corresponding to an area located entirely on the right side of the curve. Right side of the curve is also a positive z-score. And that will conclude section 6.2.